this presentation, I, Eitan Kalfa, and my team will be discussing our proposal focused on agrovoltaics and bifacial solar panels. We'll explore how these technologies work together and maximize land productivity by combining energy generation and agricultural use. This property in Wooton is large and remote, with limited infrastructure and patchy internet. The owners want a sustainable and reliable system that supports off-grid or hybrid living. With sunlight, wind, and water availability changing seasonally, we need a flexible multi-source solution. A long-term cost effectiveness is a major factor here.
The property owners are the primary stakeholders. The local council regulates all infrastructure. Energy companies manage the supply and the price of the energy provided. The equipment suppliers are responsible for delivering parts and providing warranty for those parts. And the local community may raise concerns over noise or ecological problems. The communication protocols include bi-weekly meetings with the client that updates them on the progress and quality of the project. Monthly reports will be shared with all stakeholders, and weekly internal teams check-in will track the progress and task updates. Risk and uncertainties around the project include political, which are changes in government support, economical, which are the budget overruns and fluctuating prices, social is if the community supports the project or not, technological is the reliability of technology and how reliable it is and the safety regarding cybersecurity. Legal is a compliance with council regulation. Until the council does not approve, you cannot start building. Environmental is the weather will fluctuate, which will affect the energy generation.
This here is a sustainable energy system, and it uses bifacial agrivoltaic panels in a DC coupled setup. A solar charge controller manages power flow to a battery bank and a multi-mode inverter, which converts DC to AC electricity. It is then distributed via a switchboard to the house, sheds, and grid, allowing for efficient energy use, storage, and two-way grid interaction. This here is our energy system follows a clear sustainable framework. It uses solar and agrivoltaics to cut emissions and improve land use. Economically, it lowers power bills and uses efficient bifacial panels for better returns. Socially, it boosts energy security and sets an example for sustainable living. This ensures reliable energy while supporting long-term sustainability.
Today, we are going to be presenting 4 innovative energy solutions ideal for off-grid living. Firstly, we need to decide how these energy solutions are going to store their energy in an effective, environmentally friendly way. Here are the pros and cons of lithium and hydrogen batteries. Lithium-ion batteries offer high energy storage and are easy to install, but raise ethical concerns with how they're made and require replacement every 10 years. Hydrogen storage emits only water vapor and stabilizes energy supply, though it's costly and needs specialized systems. Here are our 4 design solutions. Bifacial agrivoltaic solar panels. They capture sunlight on both sides and let farming continue underneath, boosting land use. Wind turbines. They generate power all day and night, but rely on local wind and face massive zoning challenges. Geothermal heat pumps provide year-round heating and cooling, cutting energy bills by up to 60% with minimal emissions. Lastly, solar combined with micro hydropower offer continuous energy, perfect for properties with flowing streams. Together, these systems enhance energy resilience and sustainability and off-grid independence. Next to Luke with life cycle costs.
Thanks, Eden. Next, we considered life cycle costing, in which we considered 4 main energy system solutions and their features in order to meet the parameters outlined in the call to proposal. We broke down the project into 3 distinct stages to create a framework for an effective costing to be made, including the acquisition phase, operation phase, and the end of life phase. Then we gathered data including estimated usage, equipment costs, rebates and credits, feed-in tariffs, discount rate, and inflation rate. From this, we calculated net cash flow per year and evaluated the net present value, NPV, which we used to compare costs across alternatives on a consistent economic basis, which is especially important when systems have high upfront costs but long-term savings, such as the solar or geothermal pump. The result of such gave us a final comparable figure in which we could evaluate the design alternatives, and resulted in our choosing of the agrivoltaics bifacial solar panels as our final design solution.
Hello, I'm Gabriel, and I'll be explaining our life cycle analysis that was conducted. We have 4 parts of life cycle analysis, being our scope and definition, inventory analysis, impact assessment, and interpretation. Our goal, scope, and definition is to create a sustainable energy system that best provides the electrical needs of the property that is specified by the clients in the call for proposal. Next is our inventory analysis. We focus on measuring and categorizing key parameters for each design alternative, considering geographical data such as temperature, precipitation, UV intensity, and wind speeds. And we formulated them into a table so they can best grasp the overall value of each design alternative based on these measurables. Our impact assessment covered both the effects of global warming and resource depletion. Each of our design alternatives adhered to the reduction of global warming, as each system produced 0 kilograms of CO2 per year. Additionally, we looked at lithium battery storage and water usages within our sustainable energy system designs. All systems had minimal impact toward lithium pollution and water usage. Thus, our impact assessment proved to show that each system does not exhibit any unwanted impacts to the environment. And finally, using both our findings of the life cycle analysis and the life cycle costs, we can interpret this data to settle on a final solution. And I'll let Mark talk more about that on the next slide.
Thanks, Gabriel. To determine the most suitable energy solution for the Wuton property, we conducted a multi-criteria decision analysis using 5 weighted factors: cost, energy efficiency, reliability, environmental impact, and maintenance. Wind turbines scored high on efficiency but were limited by high maintenance and low reliability due to possible inconsistent wind speeds. Geothermal heat pumps had strong reliability and energy efficiency, but also had a very high upfront and maintenance costs, which could possibly be difficult for the family to manage. The bifacial solar and micro hydropower hybrid offered excellent reliability, but suffered from environmental impact and high upfront costs from the installation of the microhydro system. As a result, the bifacial agrivoltaic system achieved the highest weighted score as it maximized ethical and environmentally safe energy production, whilst also supporting crop management, thus making it the best design solution